which components you have in your water are one thing, but then the type of water you have, that's the second very important factor. So the levels of both ozone and radicals are completely dependent on your matrix. So this means if you look at surface water, wastewater effluent, or even waters after RO, you have some people in the food industry, or you have other industries as well. For example, aquaculture that apply ozone. Well, it all looks very different. So let's look at this kinetic fact, so the matrix. This is on the slide. What you see here is a simple banded pipe. It's a pipe, and ozone is dosed at the start, and it flows out to the right. It's 4 times the same pipe. But what we visualize at the left is secondary effluent, let's say a very reactive matrix, and a less reactive matrix at the right, which is, for example, drinking water or surface water. The top row shows the local ozone concentration, and the bottom row shows the hydroxyl radical concentration locally in this pipe. So this is a computational fluid dynamics simulation. To be sure, it's a 3D pipe. Well, what you can see is that ozone depletes very fast in secondary effluent, while it survives way longer in drinking water, of course, leading to much higher CT value. Yeah, obviously. Look at the radicals. It has a huge impact as well, because you produce quite some radicals in the beginning, while in drinking water, you also have some radicals, but the levels are generally much lower. So this is the impact of the matrix. So if we now combine it, the matrix with the reactivity of components, we get these kind of plots. And here we visualize the same pipe, but we compare 1,4-dioxane with diclofenac, for example. And what you can see is in a very reactive matrix where you produce quite some radicals, you have significant removal in 1,4-dioxane, but let's say you get until 40% removal or so. For diclofenac, it doesn't matter. It is 100% removed after a few milliseconds to a few seconds. And this is what you clearly see here. Red is 100%, and it's already dark blue, even at the start of the pipe. While in drinking water, it's much more difficult, this one. In this case, so it's very matrix dependent. But we are just visualizing here, if you have a pipe of, let's say, 1 meter of length, well, this is the consequence of your removal of target pollutants. And the third one that is very important is bromate. If we are looking at ozone, bromate is always a variable of interest. In the end, you go from bromide to bromate. Just neglect what is in between here. It's quite complex. We will not show too much here. But just remember that there are 2 pathways. Bromide either reacts with hydroxyl radicals or it does with ozone. And this leads ultimately via a few intermediate steps to bromate. So again, this is very important. So we will now go back to Giacomo, and he will go 1 level deeper with the batch now, starting to compare 2 very different waters.
Yes. So let's go a bit deeper in the story. So what you see here is again our 2 beakers, in which in one we have surface water. So like imagine it very clear, low organics, low ammonia, almost none, and low alkalinity and so on. And a sample instead in the second beaker with secondary effluent, with quite some more organics left over from the upstream wastewater treatment plant, some ammonia left, some nitrite, some nitrate, and so on. So what happens to the profile of ozone? So here we have the profile we have just seen of the surface water. Let's look at the secondary effluent ozone profile. So as you can see, in few seconds, in about 6 to 10 seconds, the ozone gets completely removed. So it reacts with the water matrix, and it gets depleted much faster than in the surface water sample. So let's look now at what happens in terms as a result of all these reactions with organics and inorganic fraction of the water matrix. What happens to the hydroxyl radicals? So we have seen our radicals generated in a matter of milliseconds in a peak concentration here from the surface water sample. And here we see again also the secondary effluent concentration of radicals. So as you can see, it's much lower. And the reason why this is much lower, it's a consequence of a very complex net of reactions in which you have higher production, but also higher scavenging. And at the end of the story of hydroxyl radicals. So you do produce more radicals because the reactions are faster and imply a larger amount of ozone consumption, but you also scavenge more because of more inorganic carbon content or more organic carbon content that does the same job, and so on. So what is this? The consequence in UVA? We see it here that our UVA content in the secondary effluent sample, it's generally much higher than the surface water. So you have more organics to destroy, but most importantly, what happens in terms of micropollutants. So if we look at the carbamazepine and diclofenac profiles, and we add the profiles with the small dots regarding the secondary effluent, we see that they're disappearing still in the first few milliseconds to seconds in our beakers, because they are very sensitive to the initial ozone concentration and both also the radicals. So keep that in mind. And what we can look at here as the difference between the diclofenac in surface water and diclofenac in the secondary effluent. So they practically behave in the same way because it's due to its very high sensitivity to ozone and radicals present. Carbamazepine also reacts in a very similar way in both samples, slightly slower one, if you can say so. It's really a matter of milliseconds here in the secondary effluent sample. But the story changes if we look at metformin. Metformin is very, very sensitive only to radicals, not to ozone, and the residual ozone doesn't have almost any impact on metformin. And the fact that we have less availability of radicals because of the higher scavenging in the secondary effluent sample makes metformin really difficult to be knocked down in the secondary effluent. Finally, if we look at metoprolol, the picture is even more different here between the surface water sample, where metoprolol was removed just as a matter of time, because that is still sensitive to ozone, other than to the radicals. But what happens in the secondary effluent sample is that ozone gets depleted in the first, remember, in the first 6 to 12 seconds here, the aqueous ozone in the secondary effluent, it's consumed, and then as a result, you have metoprolol residuals. So you are not able to remove it anymore. And also the radicals are gone as well. So finally, we can look at the bromate levels, which look very different also for the surface water sample and the secondary effluent sample. So what is the difference? The main difference here is that as a result of a very complex and long list of reactions that end up eventually in bromate, very important is the availability of radicals to trigger these reactions and the availability of ozone. You remember what Wim just mentioned about the two ways of starting up the bromate formations that you can have, either way with radicals or with ozone. Well, In the secondary effluent sample, you have limited possibility there because both are being depleted very fast. So this is mainly what is about the difference that we are observing here. And now, before we go more in detail, we go back to Wim, and we see each other shortly for the next demo.
Maybe Wim, if I can jump in, there have been some questions. One of them is if we assume complete oxidation or if we also look at the breakdown products. And the other one is concerning the previous slide with the pipe. If there are more hydroxyl radicals and ozone in the drinking water pipe, why is the contaminant on the top of the previous slide or not removed? So maybe you can quickly answer those two questions before continuing.
Okay. Yeah, very relevant questions. So the first one is a question we get more and more often. We didn't expect it because we expected that people in the first place would be focusing on the target contaminants, but indeed more and more people are concerned about the byproducts. And the good news is, well, they are not currently in the model because we have been focusing on the first priorities in the market. But we definitely have plans to include some breakdown products because so much nice research has been done. And for many of these target contaminants, the yields and also the production rates and which byproducts are being formed, they are known. So we can easily extend our model with it. So that's definitely possible. Second question, well, it is important to notice that the slides, the simulation Giacomo has shown, comparing secondary effluent with drinking water, they were completely different matrices than the one in this slide. So it's highly dependent on the matrix. So let's not generalize that you have more radicals in drinking water compared to wastewater and reverse. It really depends on the case. In this specific case on the slide right now, you had actually either a lower production of radicals or a higher scavenging of radicals in let's say the less reactive matrix, which is the drinking water. Yeah, this is what you can see here. So it's really matrix dependent. We can give the definite answer definitely if you send us an email. Then we can really say it why it's happening. So let's conclude on this kinetic side because then we go to probably the most interesting one, which is piloting and full-scale application. First conclusion is the removal of target contaminants or organisms is dependent on their sensitivity towards ozone and radicals. So just think about the skins again, very sensitive versus very resistant, let's say. And then also the levels of ozone and hydroxyl radicals are highly dependent on the matrix. So these are really, really very important things that drive how ozonation or advanced oxidation will perform.